Now I would like to explain about magnification in series resonance and parallel resonance. So first, magnification and resonance. If you assume the voltage applied to the series RL circuit V and the current at resonance is I, then the voltage across the inductor. Okay, voltage across the inductor is VL equals to I into XL. So at resonance current equals to I. XL is inductive reactance. So voltage across the inductor VL equals to I into XL. So we know that I equals to V by R and XL equals to omega into L. At resonance frequency omega equals to omega suffix R. So it equals to V by R into omega R into L. Similarly, the voltage across the capacitor VC equals to I into XC. Here I current at resonance, XC capacitor reactance at resonance. I equals to V by R and XC equals to 1 by omega R into C. So VC equals to V by R into omega R into C. So the quality factor Q equals to formula 1 by omega R into C into R, or it equals to omega R into L by R. This is the quality factor formula. So for RC circuit quality factor, for RL circuit quality factor formula. So where omega R is the frequency at resonance. So finally we can write VL equals to VL equals to V into Q and VC equals to V into Q. So 1 by omega R into C into R equals to Q, omega R into L into omega R into L by R equals to Q. So VL equals to V into Q, VC equals to V into Q. So from this equation we can write the magnification factor Q equals to, or quality factor Q equals to VL by V or VC by V. So the ratio of the voltage across the either inductor or capacitor to the voltage applied at resonance can be defined as magnification. Here Q is magnification. So Q equals to VL by V or VC by V. Okay, next one, parallel resonance. Okay, this is parallel RLC circuit. Here I be the current flowing in the circuit, so input current, and IC is the capacitor current, IL is the inductor current. So this branch current is IC and this branch current equals to IL, and capital E is applied voltage. So from the above circuit, so we have the impedance of branch 1. Here two branches are there. This is first branch and it is second branch. In a parallel circuit, at resonance condition, the net susceptance equals to 0. So in series RLC circuit at resonance condition, the net reactance equals to 0. So similarly in parallel RLC circuit at resonance condition, the net susceptance value equals to 0. So susceptance means reciprocal of reactance. Okay. So first one, first branch impedance. This is the first branch. Here first branch having only capacitor. So we know that the capacitor reactance equals to XC. So Z1 equals to XC and XC equals to 1 by J omega C. So admittance equals to 1 by impedance. Y1 equals to 1 by Z1. So it equals to 1 by J omega C equals to J omega C. Okay, this is first branch admittance. Okay, this branch admittance equals to Y1. So next to second branch admittance. Here second branch is series RL circuit. Series RL circuit. So Z2 equals to R plus J into XL. Z2 equals to R plus J into XL. So now admittance, Y2 equals to 1 by Z2, it equals to 1 by R plus J into XL. The admittance equals to reciprocal of impedance. Here we have to set susceptance equals to 0. So susceptance is present in admittance form. So that's why here we have to first find the admittance. So first branch admittance equals to Y1, second branch admittance equals to Y2. So next to total circuit admittance Y equals to Y1 plus Y2. So by simplifying this equation we get Y2 equals to this one. So Y2 equals to 1 by R plus J into XL. So into R minus J into XL by R minus J into XL. So Y2 equals to R minus J into XL by here A plus B into A minus B formula, A square minus B square. So R square minus J square into XL square. So J square equals to minus 1, minus into minus plus. Okay, minus into minus plus. So denominator R square plus XL square. So now the total admittance is given as Y equals to Y1 plus Y2. So Y equals to first branch admittance J omega C. Y2 equals to R minus J into XL by R square plus XL square. So it equals to r by r square plus xl square plus j into omega c minus j into xl by r square plus xl square. It equals to r by r square plus xl square minus j into xl equals to omega into L. So omega into L by r square plus xl square minus omega c. The parallel resonance is also called as anti-resonance. Anti-resonance. So at anti-resonance, the imaginary part will be equals to 0. So in admittance form, real part is conductance and imaginary part is called susceptance. So here imaginary part is susceptance. So at resonance condition, in parallel RLC circuit at resonance condition, the net susceptance value equals to 0. So by equating this imaginary term equals to 0, we get next equation. So minus j into at anti-resonance omega equals to omega suffix ar. So omega ar into L by r square plus omega ar square into L square minus omega ar into c equals to 0. It equals to omega ar L by r square plus omega ar square into L square minus omega ar into c equals to 0. It equals to omega ar L by r square plus omega ar square into L square equals to omega ar into c. Here omega ar cancel. So L by r square plus omega ar square into L square equals to c. Or r square plus omega ar square into L square equals to L by c. Omega ar square into L square equals to L by c minus r square. So next equation, omega ar square into L square equals to L minus cr square by c. Omega ar square equals to L by cl square minus cr square by cl square. Omega ar square equals to 1 by lc minus r square by l square, or omega ar equals to square root of 1 by lc minus r square by l square. So we know that omega equals to 2 pi f. So 2 pi f ar equals to, so square root of 1 by lc minus r square by l square, or far equals to 1 by 2 pi square root of 1 by lc minus r square by l square. Okay, this is the resonance frequency or anti-resonance frequency. Okay, resonance frequency of parallel RLC circuit or anti-resonance frequency formula. Okay, for this circuit, resonance frequency formula. Okay, for any circuit, in this way we have to determine the resonance frequency of parallel circuit or anti-resonance frequency. So first we have to write impedance equation. Next, by using impedance equation, we have to write admittance equation. In admittance equation, by equating the imaginary term equals to 0, we can determine the resonance frequency of circuit, parallel RLC circuit or anti-resonance frequency. So finally this is anti-resonance frequency of the above circuit. So next one, expression for quality factor and bandwidth in parallel resonance. So this is one parallel RLC circuit. Here RLC connected in parallel connection, applied voltage equals to V. Okay, so we know that at a resonance condition, the net susceptance equals to 0 in admittance form. In admittance form, Y equals to G plus JB. So impedance form, Z equals to R plus J into X. Similarly, in admittance form, Y equals to G plus JB. Here G is called conductance and B is called susceptance. So admittance equals to 1 by R plus J omega C plus 1 by J omega L. Here three branches are there. First branch. So first branch impedance equals to R, admittance equals to 1 by R. Second branch impedance equals to J omega L. Second branch impedance equals to J omega L. So admittance equals to 1 by J omega L. 1 by J omega L equals to 1 by J omega L. So next third branch impedance equals to 1 by J omega C. Okay, third branch here capacitor reactance equals to XC equals to 1 by J omega C. So reciprocal of 1 by J omega C equals to J omega C. So here three branches connection, parallel connection. If three branches are connected in parallel, then equivalent admittance equals to, so sum of the individual admittances. So first branch admittance 1 by R, second branch admittance 1 by J omega L, third branch admittance J omega C. R it equals to 1 by R plus J into omega C minus 1 by omega L. So 1 by J equals to minus J by omega L. By taking J common, we can write 1 by R plus J into omega c minus 1 by omega L. This is equation number 1 and it is equation number 2. So we know that at resonance condition the net susceptance value equals to 0. So by equating this term equals to 0, omega rc minus 1 by omega r equals to 0, or omega rc equals to 1 by omega rl, omega r square lc equals to 1, omega r square equals to 1 by lc, omega r equals to square root of 1 by lc, or fr equals to 1 by 2 pi root lc. So for this circuit, this is resonance frequency. Okay, in previous circuit, so capacitor in parallel connection, resistor and inductor in series connection. So for this circuit, so this is the resonance frequency, and for this circuit, this is the resonance frequency. Omega r equals to 1 by root LC, or fr equals to 1 by 2 pi root LC. So the next one, so voltage current variation with frequency. So in parallel RLC circuit, at resonance condition, the net susceptance value equals to 0. So in that case, y value equals to 1 by r, y equals to 1 by r. So at resonance condition, here the admittance value equals to minimum value. If admittance is minimum value, impedance is maximum value. So the relation between impedance and admittance is reciprocal inverse relation. If admittance is low, impedance is high value. So here y equals to 1 by r plus j into omega c minus 1 by omega L. So at resonance condition, this term equals to 0. So y equals to 1 by r. So it means at resonance condition, the admittance value minimum value, so impedance value maximum value. If impedance value high value, current value becomes minimum value. I equals to voltage by impedance. If impedance is high, current is low. So finally in parallel RLC circuit, at resonance condition, the current is minimum value. So initially below the resonance frequency, the current value high compared to the current at resonance frequency. So initially current value high value. So by increasing this frequency value, the admittance value decreases. So finally it reaches to minimum value at resonance frequency. Okay, finally at resonance frequency the admittance reaches to minimum value. In that case the current also minimum. Again after resonance frequency the admittance increases, current also increases. So this is the current variation with frequency. So next voltage. See voltage at resonance frequency is maximum value. So next the bandwidth. We know that bandwidth equals to f2 minus f1. Here f1 F2 are called half power frequencies. So f1 is lower cutoff frequency, f2 is upper cutoff frequency. So previously we derived this relation in series RLC circuit, the same relation. Here also at half power frequencies, the current value is 1 by root 2 times of current at resonance. 1 by root 2 times of current at resonance. By using that relation, we can write omega 1 into C minus 1 by omega 1 into L equals to minus 1 by R. Let equation number 3. Or omega 1 into C plus 1 by R equals to 1 by omega 1 into L. So from this equation we can write omega 1 RC plus 1 by R equals to 1 by omega 1 into L, or omega 1 square RLC plus omega 1 into L equals to R. Omega 1 square RLC plus omega 1 into L minus R equals to 0. So by taking RLC common, so RLC into omega 1 square plus omega 1 into L by RLC minus R by RLC equals to 0. So the equation omega 1 square plus omega 1 by RC minus 1 by LC equals to 0. Equation number 4. So next to find the roots for this equation. So by using formula minus b plus or minus square root of b square minus 4ac by 2a. Here b equals to 1 by RC, a equals to 1, c equals to minus 1 by LC. So formula minus b plus or minus square root of b square minus 4ac. So by using that formula find omega 1. So finally the roots of this equation, omega 1 equals to minus 1 by 2 RC plus square root of 1 by 2 RC whole square plus 1 by LC. So similarly at upper cutoff frequency, so we know that the inductive reactance value I value, so XL value greater than XC. So omega 2 minus omega 2 into C minus 1 by omega 2 into L equals to 1 by R. Okay, at omega 2 means upper cutoff frequency. At upper power frequency, this is not correct. So XL value far less than XC, or XC value greater than XL. So in that case omega 2 into C minus 1 by omega 2 into L equals to 1 by R, or omega 2 into C minus 1 by R equals to 1 by omega 2 into L, or omega 2 into RC minus 1 by R equals to 1 by omega 2 into L. Okay, this is XC greater than XL. So next equation, omega 2 square RLC minus omega 2 into L equals to R, or omega 2 square RLC minus omega 2 into L minus R equals to 0. So by taking RLC common, omega 2 square minus omega 2 into L by RLC minus R by RLC equals to 0, or omega 2 square minus omega 2 by RC minus 1 by LC equals to 0. Okay, equation number 5. So next to find roots. So by using formula minus b plus or minus square root of b square minus 4ac by 2a, here a value 1, b equals to minus 1 by rc, c equals to minus 1 by lc. So finally here omega 2 equals to 1 by 2 rc plus or minus square root of 1 by 2 rc whole square plus 1 by lc. So the bandwidth equals to formula f2 minus f1, or omega 2 minus omega 1. Already we find omega 1 and omega 2. So by using omega 1 and omega 2, so find omega 2 minus omega 1. So we get 1 by RC. So the bandwidth omega 2 minus omega 1 equals to 1 by RC. It is bandwidth. So next the quality factor. So quality factor equals to omega R by omega 2 minus omega 1, or FR by F2 minus F1. So FR is resonance frequency, F2 minus F1 by bandwidth. Resonance frequency by bandwidth equals to quality factor. So the quality factor at resonance condition equals to omega R by omega 2 minus omega 1 equals to 1 by RC. So it equals to omega R into RC. This is the quality factor at resonance condition. So at resonance condition, the quality factor Q suffix R equals to omega suffix R into RC.